All right, so we just learned about this really new and interesting carbocation rearrangement situation. It just blows our mind, and it's really cool and exciting. But what was the deal with all the substitution and elimination chemistry we learned with alkyl halides in chapters 7 and 8? Turns out in those chapters we deliberately picked only examples that wouldn't rearrange. And that allowed us to learn about those concepts without needing to worry about the rearrangements yet. But where are we now? Well, we know when different types of chemistry is going to happen. And now that we know about carbocation rearrangements, we can kind of add that piece into the puzzle. So we have two different situations here, same alkyl halide, different conditions. So what I want you to do is figure out what's going to form in each of these, pause the video, try that, and then come on back. All right, great. You did that. Let's talk about the first one first. We got our potassium tert-butoxide, DMF. DMF is our polar aprotic solvent, that increases the rate of bimolecular reactions. It doesn't actually make a difference as far as is it going to be bimolecular or unimolecular. It just increases the rate. But is it going to be bimolecular or unimolecular? Well, is potassium tert-butoxide a strong or weak base/nucleophile? It is charged. It is strong. This oxygen is a very strong nucleophile. It's charged. It's reactive. What's it going to do? Well, charged strong nucleophiles, which you'd have to go back for us to get the full definition of a strong nucleophile, but oxygen negatively charged is always a strong nucleophile/base. What about this one? What's the T-butyl like? Well, we got the oxygen with the three big CH3 groups. It's a strong nucleophile/base, but since it's so bulky, it's so hindered, this is the scenario where we can only do elimination because it cannot get to the back side of that alkyl halide where it needs to get. So this set of conditions is going to favor E2 exclusively, and we're just going to pull off that proton and form our major product, which is that tri-substituted alkene. Did anything change here now that we know about carbocation rearrangements? No. Why was that? Because no carbocation ever existed in these reaction conditions. If there's no carbocation, then carbocation rearrangements don't really matter. So that's that situation. What about this one here? Well, we have a weak nucleophile/base. This time, weak nucleophile/bases, they wait around for reactions to be more favorable. They always go through unimolecular processes. And when E1 happens with alkyl halides, SN1 also happens. So this is going to be E1/SN1. So why do these carbocation rearrangements matter? Well, for the SN1 product, we would have formed our carbocation. That would have been like that. It's a secondary carbocation. This would rearrange then. This hydrogen would pop over there to form the more stable tertiary carbocation. And at that position, we would get our E1, our elimination, and our SN1. So the final product of this reaction is going to be a mixture of the SN1 product and the E1 product, which again is going to be a mixture of tri-substituted alkenes. So knowing about these carbocation rearrangements changes our product distribution a little bit. We would have expected to have the OCH3 there if we didn't know about carbocation rearrangements, but this isn't a whole new concept, right? What we have to always focus on is rearrangements happen anytime a more stable carbocation can form from a less stable carbocation. So really all that's new here is every time we see a carbocation, we have to take a break, sit back, say, you are a blank carbocation. Is there an option for a 1,2 alkyl or 1,2 hydride shift for you to become more stable? If yes, it's going to occur. If no, it's not going to occur. So alkyl halides, alcohols, anytime we have these carbocations form, we have to think about that rearrangement possibility.